Hello everyone and welcome to your video lesson of physics. So today in this video I'll be quickly going through some of the content of magnetism and electromagnetism. And after that I'll be solving some of the most recent past paper questions from this topic. So the primary task or the primary reason for the video is to solve the most recent past paper questions, but just for like a prerequisite, I'll be going through some of the content. All right, it won't be a detailed lecture about the content. If you want the detailed notes of it, I shared the link in the description. You can download the worksheet from there. But the main target of the video would be to solve some of the most recent past paper questions. So let's start with it. All right, so the chapter starts from the magnet and its magnetic properties. All right, here I'll be having just a kind of a flashcard overview, just some bullet pointers, the very precise notes for the entire content, right? And again, we'll not be going into the details, not much into the details, but just for some of the bullet and some of the pointers. What are the two poles of a magnet? Well, a magnet has a north pole and a south pole, right? So no matter if, let's say if you have a magnet, a north pole and a south pole, and by some way you try to, or you eventually manage to break down that magnet, right? Let's say you break it up from here. Now the small or the submagnets, they would behave like an independent magnets with a set of north pole and south pole. So a magnet would always have a north pole and a south pole. How do these different poles of magnet interact? Now this one is very uh, straightforward, that the opposite poles attract, or unlike poles attract, and like poles repel. All right, just like the charges, same as of the charges. Okay, and one thing you can even consider your mind from here, that for charges, same charges would repel, same magnetic poles will repel, but same currents, which is a fact that we use in upcoming topics as well, same currents would attract. Like for current, it would be the other way around. And basically, we will study that it's not that the currents are actually attracting or repelling each other. No, current would not itself be doing that thing. It is the magnetic field that is produced in consequence of that current which attracts or repels. Now the magnet can be divided into two types, or the magnetic material. First of all, a permanent magnet. A magnet that has its own magnetic field, and it would be either repelling or attracting the other magnets. It would be made up of magnetic material, and you cannot demagnetize it. This is what a permanent magnet is. If there is something which is not a permanent magnet, temporary magnet, you can demagnetize it. There are a lot of ways by which that magnet can be demagnetized, but a permanent magnet cannot be demagnetized. Now there are two types of materials: magnetic materials and non-magnetic materials. Then we have the magnetic materials subdivided into soft magnetic materials and hard magnetic materials. So it looks something like this: materials, writing here materials, then we'll be having magnetic, then we'll be having non-magnetic, then magnetic materials would further be divided into two components, two branches, two sub kind of materials: soft magnetic and hard magnetic material. Primary example of soft magnetic material is iron, soft iron if you want to be precise. The primary example of hard magnetic material is steel. There are a lot of other examples, but this is the one that is often used. Non-magnetic material like aluminum, copper, and basically all the non-metals are straight away non-magnetic materials. So what is the hard magnetic material? Hard magnetic materials are the ones which are difficult to magnetize and difficult to demagnetize. Difficult to magnetize and also difficult to demagnetize. But once you magnetize them, they will be behaving like a magnetic material for a long time. If we talk about the soft magnetic material, the soft magnetic material, you can consider your mind easy come, easy go. You can make them magnetic quite easily. You can magnetize them quickly, but you can, or they'll be demagnetized quickly as well. So it's just like a battery which is almost out of order. It would be charged quickly, but then at the same time it would be discharged or drained quickly as well. So these are the soft magnetic materials. Once again, the primary example is iron. Some of the examples of, magnetic materials, sorry: iron, cobalt, nickel, steel. Among these four, steel is the one which itself is not an element. It is a mixture of element that we call alloy. It consists of iron and a percentage of carbon as well. Then we have magnetic field, just like we had electric field in case of a charge. Right, in case of, let's say, positive charge, we have some zone, some region, a premises around which another charge would experience a force. Let's say we have another charge plus q over here. the, that charge would experience a force, electric force in that case. Likewise is the case of magnetic field. If you have a magnet, in the region around that magnet, another magnet will experience a force. So that region is called magnetic field. All right, keep in mind the magnetic field term is used for that region, the premises, the surrounding region in which another magnet, in which another magnet or a magnetic material would experience a force. Which direction do the field lines in magnetic field point? Electric fields lines point from positive to negative, positive charge to negative charge. And magnetic field lines emerge from North Pole and they are directed towards the South Pole. Does a high concentration of field lines mean the field is strong or weak? If you have more magnetic field lines at a place, that would imply that the magnetic field at that point is strong. Okay, problem with the next one page. Okay, let's skip this one for a while. Okay, true or false? Magnetic field lines never cross each other. Is that true or false? That is true. The reason is, if the magnetic field lines, let's say there's a magnetic field line in this direction and then there's a magnetic field line in this direction, right? Now that would imply that at this point, at the point of intersection, let's call it point A, that would imply that at point A there are two directions of magnetic field lines, which is not possible. More than one direction. So that would mean, let's say if you have a positive charge over here, let's call it plus Q, and you place that positive charge over here at the small black dot, then the positive charge would move in this direction and at the same time in this direction, which is practically not possible. The charge, sorry, in that case we are talking about the magnetic field. So if you place a north pole over here, north pole of another magnet over here, so on that north pole of another magnet there has to be only one direction in which force can be applied. There can't be two directions. How can you produce uniform magnetic field? Uniform magnetic field, on paper you represent uniform magnetic field with the help of parallel lines. See, that one represents uniform magnetic field. So the lines should be parallel, parallel lines and equidistant lines. Alright, two consecutive lines should be having the same distance. Alright, equidistant, any two consecutive lines should be equidistant. They should be separated by a fixed distance. How is a plotting compass used to map out the magnetic field? There's a procedure for that. You place the compass, let's say this is your magnet, you want to find the direction of magnetic field. This is north pole, this is, you place the compass somewhere over here, compass will point in a certain direction, then you place a dot over there, then place the next compass or the same compass on that dot. The compass needle would point somewhere, put a dot over there, place the compass once again, then join all the dots, you'll get a field line, then you do same thing in different directions, you will get a complete pattern of magnetic field. And there's another way as well by which you can find the direction of magnetic field. That method is called iron sprinkle method. So basically you place a bar magnet under the sheet of paper, throw the iron sprinkles on that. The iron sprinkles will align themselves in a certain way, and that way would represent that pattern would represent the magnetic field. There's a problem with that method, not a problem but a limitation, that with the compass method you can find the direction of magnetic field as well. You would actually know that if this is a line, you would actually know that the line points from this position to this position, because compass would tell you the needle of the compass will point somewhere. But with the iron sprinkle method, you'll get only this thing. All right, this is what you get with the compass, and this is what you get with iron sprinkle. Now you're not sure if the line has to be drawn forward or the magnetic field line is pointing backward. So you're not sure about it with iron sprinkle method. What must happen for a circular magnetic field to be created around a wire? The current has to flow through it. All right, basically, and this is the thing where the rules start from. So you could call them hand rules. This is where the rules start from. So, and just a quick introduction, if you have cross over here that represent current, and they say cross represent current, then that would mean the current is flowing inward into the page or away from you. If you're looking at that on the sheet of paper, it is moving away from you into the paper. If you're given with the dot, that implies the current is emerging out of the paper. And for both, we have magnetic field pattern, which is determined by the right hand rule. In that rule, I'm not once again, I'm not going into details, but I can tell you, like in that rule, you have to point your thumb in the direction of current. The fingers will curl in the direction of magnetic field for the right hand. Has to be applied with the right hand. All right, let's move on. Then you have Fleming's left hand rule, FBI rule. Okay, so why do we use this one rule? This left hand rule is generally used to find the direction of force acting on a current carrying conductor. Now, how do we use it? Well, you use 3.3 fingers of your left hand in a way that they are perpendicular to each other. All right, and the thumb and the forefinger should form an L shape. All right, you cannot twist it like that. These three are also perpendicular, but it's not forming an L shape between thumb and the index finger. So first of all, you align your forefinger in the direction of magnetic field, you align your middle finger in the direction of current, then automatically your thumb will point in the direction of force. So basically, current, magnetic field, and force, they all act perpendicular to each other. All right, and this is a very important step. It can, like, if you have to find the direction of force in a certain case, it would actually you can reduce the possible directions to basically 2. You can reduce from 6 possible directions, you can narrow it down to only 2 directions. If you know this thing, that current, magnetic field, and force all act perpendicular to each other. How can we increase the magnitude of force? Basically, you can increase the amount of current, you can increase the strength of magnetic field by using a bigger or stronger magnet, you can increase the size of the conductor. Now in that case you can increase the amount of force. Oh, sorry, you have to place the conductor perpendicular to magnetic field. In that case the force acting on it would be maximum. What does that mean? Let's say this is the North Pole, this is the South Pole, magnetic field lines this direction, and you place the conductor in this way, and the current is like going upward. In that case the current direction of current is perpendicular to direction of magnetic field. In that case force would be maximum. Now let's move on to the questions, the main part of it. All right, here is the first one. Here is the first question now we have. Let's start with this one. I can write question number 1 over here. Figure 7.1 shows a copper wire placed on two copper rods in a magnetic field between the poles of a magnet. Okay. Crocodile clip A touches the positive terminal of the battery. This causes the copper wire to move. On figure 7.1, mark an arrow in the direction of the current in the copper wire. Alright, so this one seems to be easy. We have to mark the direction of current in the copper wire. The direction of current, the convention is the direction of current is from positive terminal of the battery to the negative terminal. So if we follow the positive terminal, this is a positive terminal that goes into the copper wire. The direction of current would be this one, upward, if you want to call it upward, or into the page or anything. It would be looking something like this. Okay. Explain why the copper wire moves along the copper rods. And this is a 2-mark question. So that's the same thing. Whenever current passes through a conductor and we place that conductor in a magnetic field, force acts on it. So let's phrase it. which is placed in magnetic field. Which is placed in magnetic field. Welcome to the lesson, Ahmed Adnan Beta. You should be noting down all the pointers, the latest question. These are the latest question from 2021, 2020 papers, which is placed in magnetic field. Force acts on the conductor on the copper wire. It's on the copper wire. And the direction of that force can be found out by using the right hand rule. Direction can be calculated found by left hand rule, Fleming's left hand rule. And what does that rule say? You can mention that rule as well. Even you can mention the direction of force as well. That in this specific case, North Pole, all right, you place your finger in that way, so the force would be acting towards left, towards this side. They haven't exactly asked you to point the direction of force, but if you want to add the direction of force, you can, because place your forefinger downward in the direction of magnetic field, middle finger into the page, then the thumb points towards left with respect to the diagram, right? Not from your perspective, but towards left with respect to the diagram. Name two different devices that use this effect. So one is DC motor, because in DC motor we use that effect to make coil, current carrying coil, rotate, and then we attach something with it, and that thing would also rotate. DC motor and loudspeaker as well. Let's move on to the next one. Now this is once again another latest question number 7 from your paper, May June paper 2 to 2021. Another recent question. It is about the DC electric motor, but all the question may not be related directly to the DC motor. Some of the parts would be from the facts that we have studied already, like a current carrying conductor experiences a force when you place it in magnetic field. The motor is connected to a battery with the positive terminal of the battery connected to the terminal A. So I can write plus over here and minus over here. The motor is connected to a battery with a positive terminal. Okay, we mark the positive terminal. Explain why the coil turns in the direction shown, which to me appears counterclockwise or anti-clockwise, whatever you want to call that. The direction of rotation is anti-clockwise. So basically, we have to explain why the coil turns counterclockwise, why not clockwise. So in this one, we use the same thing, which is the left hand rule. We have the current, which is from the positive term, from the left side, it is moving upward. You want to call it upward, you can, or you want to call it into the page, you can also call that into the page. And from the other side, it is out of the page or downward, depending on from what view you're seeing that, from the front view or from the top view. So that would be the direction of current. So on the left side of the coil, a force X on the coil, and its direction can be calculated according to the Fleming's left hand rule. So I'll be writing here on left side of the coil, coil force X, force X uh, downward, which is consistent with the Fleming's left hand rule. With Fleming's left hand rule. All right, the direction is consistent with the Fleming's left hand rule. And why the force is there in the first place? Because current carrying conductor is placed in magnetic field. Or you can say magnetic field as magnetic field due to current. All right, one magnetic field is there uh, from the permanent magnets from North Pole to South Pole. The other magnetic field is there due to the presence of current. Whenever current flows through a conductor, a magnetic field is produced. As magnetic field due to interacts with magnetic field of permanent magnets. Now on the other side of the coil, okay, on the right side of the coil, the force is upward, or you want to call it upward. Once again, it depends on your it depends on the point of reference from what perspective you're looking at the image. I would personally call it upward. On the right side of the coil, the force is upward. Force is upward as the current is reversed in that coil. With respect to left side of the coil. So downward force on the left side and upward force on the right side produces a rotation. So that's why the coil rotates in that way. And what is the direction of those two opposite forces? We have already mentioned that previously, that it is uh, uh, it is, yeah, downward on the left side, upward on the right side. So due to that, those opposite forces, the coil rotates. All right. So what I suggest is these kind of questions are quite tricky. Tricky in a sense because these are of 3 marks, and well, you never know that what kind of point you miss out, and they'll cut your mark in that. You get a mathematical question, you don't really need to worry about that, because all you can do is write down the formula, show the calculation, write down the answer with the right unit. Bingo, you get the 3 marks, 4 marks straight away. 3 marks usually. But in these kind of questions, try to be on the safer side. And what is the safer side? Try to write down the facts. Try to write down the pointers related to that concept. If you write something extra, they're not going to cut the marks for it unless it contradicts something which you have already written. All right, what I mean is, you say in the first sentence, you say force on the left side is downward. Somewhere else, you say the force on the left side is upward. That is a contradiction. So they'll cut both the sentences. All right. But if you write some of these sentences which are independent of each other and really has to do anything with the previous sentence, but it is a fact that is related to that question, you'll be getting independent mark for it. So try to write down all the facts, all the pointers, um, which is consistent with that question, right? So for 3 marks, you have to be very careful. You never know that where your mark would be cut for that. On to the next one. The turning effect is increased when the coil is wound around a soft iron cylinder. Explain why this happens. So if you wound the coil on a soft iron cylinder, all right, it would produce a stronger magnetic field, because iron is a magnetic material. It would act like a temporary magnet. It would magnetize easily, and hence you'll get strong force. First thing you can write strong magnetic field by acting like a temporary magnet. Temporary magnet. Increasing the strength of magnetic field increases the force. All right, this is an independent information that you should be aware of. The fact that if you want to increase the turning effect uh, of the motor, you need to increase the force, and in order to increase the force, you can either increase the current or you have to increase the strength of magnetic field. And also there's stuff about the orientation of those two, that they should be perpendicular and stuff. So increasing and increasing the strength of magnetic field increases force. All right, force on both sides of the coil, and hence the turning effect of the force would be increased. So just one other way to increase the turning effect of, right, like I said, that you can use a stronger magnet as well. That would do the same thing. Use a stronger magnet. Sorry, if you use a larger current or increasing the amount of current. This is one of the thing. Another one of the thing is to increase the number of turns of the coil. All right, that is another way. So that is it for this one question, which is question number 7 from paper 2 2021. All right, let's go through this one. Figure 6.1 shows the coil of a loudspeaker attached to a cardboard cone. On the pole of a stationary cylinder magnet lies near the coil. There is an alternating current in the coil of the loudspeaker. The students hear the note produced. Explain why the cone of the loudspeaker vibrates. A very generic recurrent question, and we have a generic answer for that. I mean, uh, every time they ask you, basically what they are asking you is the working of the loudspeaker. We have a generic answer for that, just like we have a generic answer for a question in which they ask you, how can you determine the pattern of magnetic field of a bar magnet? So there's a sample answer for this one as well. Every time they ask you about the working of the loudspeaker, you just write down these pointers. Straight away, you write down these pointers for 3 marks. So as the current, that case, we have the AC current. And you should be aware of the fact that AC current changes direction every half cycle. So first half cycle, the left one would be the positive terminal. Next half cycle, the left one would be the negative terminal, and the right one would be the positive terminal. And what what is it? It has to do with the in that context. Well, the direction of current determines the direction of force. Right? If you this is something that we studied, that if you reverse the direction of current through a coil, the direction of force acting on it would be reversed. So that is the key thing here. So what we write is, as the current passes through the coil, force moves the coil forward or in one direction. Force moves the coil, let's call forward, right? May not necessarily before, but we just write it for reference. Okay, for um, first case it would be forward, and then as the current changes the direction. And how come the current change the direction? Because it is AC current, alternating current. As the alternating current changes direction, force would be in opposite direction. Okay, so the force would move the coil in the opposite direction. Force in opposite direction moves the coil back in. So it would be kind of a push, then a pull, repulsion, attraction. And due to that uh, attraction, repulsion, due to that forward backward motion, due to that um, force being forward and then being backward, the diaphragm vibrates. All right, this cardboard cone would vibrate. All right, so we don't have to like get down to the point where we explain the process, or we explain the production of the sound waves as well. The diaphragm or the cone, you can write cone vibrates, right? Because we have to mention how does the loudspeaker vibrate. Then in the next part they have uh, asked us explicitly explain how the vibrating cone produces sound waves in the air. Right, that's been asked in the separate question. Now we bring that concept over here, which is as the cone vibrates, the air, all right, the atoms or the particles of the air next to the coil also vibrates, or there would be compression and rarefaction. And that compression and rarefaction propagates, right? They propagate from one place to another in the form of sound waves, in the form of longitudinal waves. So what we write here is, so we write as the coil vibrates, just give me a moment. All right, so let's write it down. As the coil vibrates, as the coil vibrates, the air particles next to the coil also vibrate. All right, it also vibrates, and this vibration is passed on from one place to another in the form of a longitudinal wave. This vibration of longitudinal wave or sound wave. All right. Then we have the next one. A strong cylinder magnet is now used. State the difference in the note heard. So now you have a strong magnet. What would happen is increasing the strength of a magnet. This is the thing that they have asked like third time now. If you increase the strength of a magnet, you can increase the amount of force. You can increase the magnitude of force, and that increased force would make the cone vibrate at a faster rate with more intensity. So the air particles would also vibrate with more intensity, and the sound note that you would hear would be louder. All right, when I say sound note is louder, it doesn't mean it has more frequency. No, frequency has nothing to do with the loudness. All right, frequency is something else. Loudness is proportional to amplitude of the sound, or amplitude of the wave, or the intensity of the wave. has greater amplitude. You can write any one of these phrases. Just a single phrase would be sufficient. Has greater amplitude, all right? Or you can also write has more intensity. Any three of these phrases would be good enough. Has greater all right, so that's it from this question as well. And let's move on to some of the paper one questions. The diagram shows a simple electric motor. The split ring commutator reverses the current in the coil as the coil rotates. The coil is rotated 60 degrees from the position shown. How many times is the current in the coil reversed? All right, so basically we study that in the working of the motor, in the working of simple DC motor, that in order to make the motor move in a single direction, make it rotate in a single direction, the current has to be flipped every time the coil uh, changes its direction, or every time the coil completes half a cycle. So what I'm trying to say is, let's say this is your side AV. The side of the coil is A, this side of the coil is B, this side of the coil is C, this side of the coil is D. All right. As the coil rotates and it completes half a rotation, what would happen is this side would now be AB and this side would now be CD. Now there comes the purpose of the split ring. You see, the coil CD would now be connected to the positive terminal of the battery, and AB would now be converted into would be connected to the negative terminal of the battery. So in terms of the angle, that is only around 80 degrees of angle, on an 80 degree of rotation, because half rotation means 180 degree, and if you complete, let's say start from here, complete the full rotation, that would be 360 degree. That would be 360 degrees. But half the rotation at this point would be 180 degree. So split ring has to change the direction of the current at 180 degree. After next 180 degree, it would change the direction of current once again. Current changes, I mean in terms of direction. 360 degrees, current changes again. So in 360 degrees, it is changing the current 2 times. All right, so in which direction the electrons are deflected? So basically we need to find the direction of the force acting on the electron. Magnetic field is into the page. You can put small crosses over here. Crosses mean the magnetic field is into the page. Then you apply the Fleming's left-hand rule and the direction of current. This is the key pointer here. If the direction of electron is forward, the direction of current would be backward. That is the basic principle of current electricity. Now, if there is a battery, current flows, right? The electrons they flow towards left. This is the electron flows to the left side, but the direction of current is from positive to negative. So the middle finger has to be backward. I'll be writing here. This is how you apply the left hand rule. Middle finger in this direction backward. Index finger should be into the page inward. And then the direction of electrons would be towards the bottom of the page. You apply the left hand rule, it would be kind of look like this, towards the bottom of the page. All right, everyone, so that's it for today. That's the end of the video. I'll be seeing you everyone in my next video lesson. Take good care of yourself.